Good day, grade 11s. We're doing chemical calculations, lesson number 4, and we're going to discuss stoichiometric calculations under the following outcomes: stoichiometry, molar volume of gases, applications of reaction that produce gases in real life situations, and lastly, we'll look at molar concentrations of solutions and do a number of examples applying all these concepts. A summary of all the stoichiometric calculations, and these are equations you need to learn to use across the reactants and products in a balanced equation, and this is very critical. The first step in stoichiometry is always to make sure you have a balanced equation. The reactants of the moles, and remember you have to work in the mole road. In other words, everything to be compared across the equation in stoichiometric calculations, you need to have it in moles. You can't compare grams and grams of two different elements. So whatever the product or the reactant is, whether it's in a gas or a concentration or a mass, so the volume of the gas, the concentration of the solution, or the mass of the solid, you need to always convert it into the moles to be able to compare across the equation. So that's why this summary is here in looking at our reactants to our products. You have to use, for instance, if you have a mass of a solid, you have to use the molar mass from the periodic table and convert it into a mole. In this one, if you have a solution and you have a concentration or a volume, you need to convert it to a mole. Or vice versa, sometimes they might give you the mole and you have to convert it back to the concentration. But we'll get to that later. And then this one, the volume of a gas, the molar volume of a gas, as the magic figure, 22,4 decimeters cubed. That is what 1 mole of every gas occupies. That's the space it occupies, the molar volume. So when we work out the moles of the gas, we're going to go through this, we will be able to take the volume that we have, we'll be able to work out, multiply the moles by 22,4 to get the volume of the gas. You can substitute into any of these equations to obviously get the mole. Change the subject of the formula and you're able to get the moles. This works for the reactants and the products, so please, these are very critical. You should know these three very, very well. Right, so I'm going to just revise through the concepts that we have learned before in the previous lesson. You should know what a mole is and the obviously the definition. But the mole is that quantity of matter. It contains the same number of elementary particles as there are in carbon atoms, 12 grams of the carbon-12 isotope. And so we have the SI unit of quantity of matter, and we know it's the mole. If we look at Avogadro's number, it's the number of particles. And so 1 mole contains that fixed number of particles known as Avogadro's number, which has a value of 6,02 times 10 to the 23. So in other words, this also applies to if they say how many molecules of water are there in 1 mole of water, and you'll have 1 mole of water contains 6,02 times 10 to the 23 water molecules. The formulas and the equations here, you really do need to be able to convert from the number of particles using Avogadro's number, and also getting to moles from the number of particles divided by Avogadro's number. So please be able to convert from the number of particles to moles and vice versa. In the molar mass, this is the one we use the most in chemistry and stoichiometric calculations. When we're converting, the molar mass is the mass per mole of the substance. And this equation, N equals little m over big M, is the fraction of the mole that you're actually getting. In other words, if I had 6 grams of carbon over 12 grams of carbon, I would have half a mole. So all we do is you actually use the mass that you actually have and put it over the molar mass, the gram per mole from the periodic table, and you will be able to work out your moles, your actual moles. This is a really critical equation, so you're able to convert from moles or mass and vice versa. So remembering that when we work on the stoichiometric calculation using the molar ratios, it must be in moles. You cannot compare masses. So you take the mass and you convert it into moles, and then you can use the mole ratios. Right, the next one is if the quantity is a gas, we have to use the molar volume of a gas. And the molar volume of a gas is N equals the actual volume of the gas, and we divide it by the molar volume 22,4 decimeters cubed, and that is the standard that 1 mole of any gas occupies, the volume, the standard volume, molar volume that every gas occupies, 22,4 decimeters cubed. So you use that as the standard at the bottom, and you're able to calculate how many moles that you have in the actual volume of gas that you're given. We will be going through this, and so this is just a summary of a revision of the concepts. Last one we're looking at is the concentration of a solution. The concentration of a solution and convert it into moles. We can't just use that across the equation. We have to get into moles. So we always look at concentration is the moles per volume, mole per decimeter cubed. So a solution concentration can be defined as the number of moles of the solute, that's the solute that's usually a solid, and we get it into moles. We can't use grams there, we have to have moles over the volume of the solution, that's the liquid. And the unit there will be moles per decimeter cubed. And so therefore, if you want to calculate moles and you're given, for instance, the concentration, which is in moles per decimeter cubed, and the volume, you can then calculate the moles by multiplying the concentration and the volume, and then you can calculate the number of moles. This is also a very important equation. So please, this one, you can use the triangle if you don't remember it, but concentration is the moles of the solute over the volume of the solution. So if you want to look at unpacking each of those, we're going to unpack the molar volume of gases and the concentrations of solutions. And the first one we're going to look at is the molar volume of gases. Now, 1 mole of gas occupies this magic figure, 22,4 decimeters cubed. And this is importantly, at standard temperature, which is 0 degrees Celsius, and standard pressure, 1 atmosphere or 101,3 kilopascals. Please, this is where most of your calculations at school level are done. So equal volume of all the gases contain an equal number of particles, provided they're at the same pressure and temperature. And this 1 mole of gas contains that number of particles, a fixed number, and it occupies the same volume. And that volume is 22,4 decimeters cubed. And so we look, this is known as the molar volume of gases, and we use that in all our calculations. Looking at a worked example of molar gases calculations. We have 2 jars of gas, one's filled with hydrogen sulfide and the other with sulfur dioxide gases. They placed mouth to mouth on top of one another in cylinders. The sulfur dioxide gas is denser than the hydrogen sulfide gas. And so the sulfur dioxide is placed at the top so that it sinks. and the gases are then mixed. And what happens is the sulfur dioxide and the hydrogen sulfide gas react, the two gases react, and it forms sulfur and water. A yellow precipitate is a sulfur like this, and it forms on the sides of the gas jars. The equation of the reaction taking place will be shown below. There are two gases here, and this is an example where if you're given, for instance here, 0.5 grams of sulfur, 0.5 gram of sulfur was produced during this reaction. So we've got a solid here and two gases. And then you asked to calculate the volume of the hydrogen sulfide gas of this reactant, reactant, and product. And now it's saying, assuming that the gases react at standard temperature and pressure. As soon as you see standard temperature and pressure, you know that you can use the molar volume of gases in this equation on this side. But what's the first step? The first step is we're given grams of this mass. So looking at this, we have to get that 0.5 gram of the solid into moles, and then we can use the ratios 2 moles to 1 mole to 3 mole to 2 moles. So this, we're only looking at the sulfur and the hydrogen sulfide. Those are the two things we asked. So we use the sulfur, the 0.5 gram, the mass there, we convert it into moles, and then we can go across the equation using this mole ratio. 3 moles is to 2 moles. We can then calculate how many moles of gas we have, and then using the molar volume, remember, the molar volume and is 22,4 decimeters cubed. So then you can convert to the actual volume, which is equal 22,4 times the mole. And so by doing this, we can actually work across the equation when we're on the mole road. So now I suggest you pause the video and you try and work it out, and then you look at the next slide to see if you did the calculation correctly. Right, the solution to this worked example on molar volume of gases. We're looking at hydrogen sulfide gas and the sulfur precipitate, the yellow precipitate. Here in this picture, there's actually a liquid solution showing the sulfur precipitate. But in gases, it's similar, with these two gases forming a yellow sulfur precipitate. In this equation, we formed 0.5 grams. That was the mass we actually formed. We were asked what volume of gas the hydrogen sulfide gas was. So we let that equal X, the unknown. Now we need to work out the comparison of the moles. So the mole ratio is critical. We cannot compare across from grams to moles. We have to all work on the mole road. So this is 2 is to 1 is to 3. We're only interested in this one and this one. So it's good to write the mole ratio below. And then we calculate the big M value, right? So from the periodic table, we go and look at molar mass. We work it out for the two things that we're looking at. The molar mass of the hydrogen sulfide gas is 2 times 1 for the hydrogen and 32 for sulfur. And you total it together and we get 34 grams per mole of the hydrogen sulfide. That's the big M. This one, the sulfur's molar mass, is 32 grams per mole sulfur. Right. That's our good starting point now, because now we see that we've got a solid over here. This solid is 32 gram per mole, the sulfur, and we can convert it into moles. So we go, the mole of N of sulfur is the mass over the big M. Mass we actually have is 0.5 gram, and the molar mass is 32 grams per mole. So we have 0.0156 of a mole. In other words, if we'd had 32 grams, it would have been 1 mole, but we don't. We have 0.5 gram. So 0.5 is a fraction of the 32, 0,0156 moles. So now we know that this reaction produced that amount of moles. Now, stoichiometrically, what would happen? How much hydrogen sulfide combines to give us that? We have to use that mole ratio to do that. So I find it's easier to say we need to get a unit mole ratio. So we need to take that mole and divide by the 3. And then we know that that's the unit mole ratio. And so we divide it by 3. And then the mole ratio is 2 of the unit mole on this side. So we multiply by 2. So now the next step is to take that value, 0.0156, divide it by 3 to get the unit mole, and then multiply by 2. So now we know we would actually have 0,0104 moles of hydrogen sulfide. But that isn't what the question asked. The question asked, what was the volume of the hydrogen sulfide gas that reacted? So now we need to go to that summary of the molar gas equation and the magic figure of 22,4 decimeters cubed, which is what 1 mole of all gases, the volume they occupy. We don't know this volume. This is the unknown that the question's asking us for. So we've made the n the subject of the formula, which is the volume divided by 22,4. And we know this. We know that 0,0104 moles. We're going to substitute that in. We know volume over the molar volume of gas at standard temperature and pressure, which we were told the reaction is taking place at standard temperature and pressure, and we divide the volume divided by 22,4. Here, we need to change the subject of the formula to the actual volume that we're getting, and the actual volume is equal to 0,0104 times 22,4. So we multiply that out and we get the actual volume to be 0,23 decimeters cubed. And this is the volume of hydrogen sulfide gas that reacted. Right, any applications of reactions producing gas in real life? And if you want to do some research, you can see airbags in cars are a common reaction that is used in producing gases. And in this case, you often find that the design of the airbag is such that a mixture of sodium azide, potassium nitrate, and silicon oxide. And then what actually happens is that nitrogen gas is released into these airbags. And this is quite an interesting reaction to research if you want to have a look at it, because there's a decomposition reaction and a gas is produced. Another one in real life where these reactions of gases are used is in ammonium nitrate explosives, where ammonium nitrate actually is used in coal mining and it decomposes upon heating and it also produces nitrogen gas. And the last one, which you're all probably familiar with, is the petrol engine. And in that case, there's a mixture of air and petrol vapor is drawn into the cylinder of the engine. And then because the piston is upward, downward movement of the piston, and the reaction, when you think about that, is your octane petrol and oxidation reaction, and it produces moles of gas far greater than the number of moles of the reactants. And this obviously results in pressure, which forces the piston down and provides power to actually turn the wheels. So molar concentrations, the next section, molar concentrations of solutions. We've now completed the molar volume of gases, and an application in real life are those 3 that I've just discussed. Now we're going to go on to the concentration of a solution, because this is also a section that applies in the same summary of moles. So we have to get from concentration to moles. So if you're given a concentration of a solution, remember it's the amount of a solute present in a certain quantity of solvent. And this in chemical terms is often referred to as the molarity. And that is moles per decimeters cubed. And molar concentration is another word for molarity. And you must remember here that 1 liter is 1 decimeter cubed. If you're given converting from centimeters cubed to decimeters cubed, please remember decimeter to centimeters, a jump of 10, and you're cubing it, so 10 times 10 times 10 is 1,000. So when you have to convert to decimeters cubed, you need to divide by 1,000. When we're converting from centimeters cubed to decimeters cubed, divide by 1,000. So please, these are also very important. If you think about what 1 milliliter is, it's 1 cubic centimeter. If you look on your ruler, 1 cubic centimeter, think of a cube 1 centimeter high, 1 centimeter wide, 1 centimeter depth. That little 1 centimeter cubed is about 1 milliliter. And if you think of 1 decimeter cubed, that's 1 liter, a 1 liter cool drink bottle, but in a cube form. Okay, so it's good to visualize it so you realize that to get from that decimeter cubed, the 1 liter of cool drink, down to that little cubic centimeter, or we're going from centimeters to decimeters, you divide by 1,000. Right, the example of 10 grams of calcium chloride is dissolved in water. This is making up a standard solution, and we're going to calculate the concentration. This can be used both ways round. You can, I can't speak this morning. Okay. Starting now. 10 grams of calcium chloride is dissolved in water and diluted to a volume of 250 cubic centimeters. Calculate the concentration of the solution in moles per decimeter cubed. So this shows you how we get a concentration, and also how you could go backwards to get the moles. If you actually had a concentration, you would then use the same equation, but substituting for the unknown, N equals C times V. So you could use this equation to get from a concentration to moles, or you could calculate the concentration of the solution if you asked for that. We will go on in the next lesson to actually use concentrations across the equation, and that we will use limiting reagents, and that will be our next lesson, lesson 5. So in this lesson, I'm just going to show you how to calculate the concentration. In limiting reagents, it is important to examine the whole equation, because what happens in reactions with limiting reagents is that some have a limited supply of a certain reagent, and therefore you have to use the reaction that produces the largest quantity, and sometimes there's an excess. So we'll be discussing that in the next lesson, because we actually have sometimes the reactant can be completely used up. When that reactant is completely used up, it is the limiting reagent. We'll be talking about that later, but standard solutions are a very important part of that. Is that if you can know, if you do a standard solution, you actually know exactly how many moles you have in that standard solution. There is a video that you will be watching at the end. There's a link for a video on making up a standard solution. But the important thing to understand is that if we need to know exactly how many moles are in that standard solution. So when we make it up, it's very precise that you weigh out an exact amount and dissolve it in an exact amount of water, so you know the dilution of it. So for instance, in this case, I would be weighing out exactly 10 grams of calcium chloride, dissolving it in 250. This is called a volumetric flask. I weigh it out exactly. I rinse all my funnel and my stirrer, and I make the solution up to a mark on the volumetric flask. This is called a standardized solution. So when we finished, we know exactly how many moles per decimeters cubed are in here, and we know that there's actually exactly 0.09 moles of calcium chloride in the standard solution. And this is critically important for when we are using equations and limiting reagents, because we need to know exactly how many moles are able to react out of that solution. So here we're going to take 10 grams of the calcium chloride, dissolving it in water and diluting it up to the volume of 250 cubic centimeters. Calculate the concentration of the solution. Notice, even though we're using cubic centimeters here, remember that's milliliters, this is liters. So we're actually going to calculate this concentration value. Right, we get the big M of calcium chloride, 40 is calcium, 2 times chlorine, and we know that our molar mass 111 gram per mole. And this is a really critical part, is this is in centimeters cubed, so we've got to divide by 1,000 to get to decimeters cubed. So the first thing we do, we calculate the number of moles that 111 grams are. The 10 gram, and this is the molar volume, molar mass, sorry, the molar mass, and we need to start all, cut in please from here. We're going to calculate the moles, and we're going to end up the mass being 10 gram, and we're going to use the molar mass 111, 10 over 111, and we divide that and we get 0.09 moles. Then we calculate the concentration by putting the 0.9 moles over decimeters, 0.25 decimeter cubed, and we get the concentration of 0.36 moles per decimeter cubed. So finally, molar concentrations of solutions are really important in chemistry. We end up often calling it the 2 molarity, for instance, of an aqueous sodium hydroxide solution, which means the same as moles per decimeter cubed. So 2 molar, or 2 molarity, as it's referred to, is the concentration in moles per decimeters cubed. Now, I suggest you also watch this video. There's a URL here to how a standard solution is made up. And we will continue in the next lesson with limiting reagents, because standard solutions are critical to know exactly how many moles of the reactant there is in the solution so that we can use it across our stoichiometric calculations. Please see the homework in the table at the beginning of the lesson and complete all think tanks or exercises.